Let us see this Fatou's lemma statement. Suppose H's mu is a measure space and f1, f2 goes on is a sequence of non-negative, this is important, s measurable function on x. Define a function f is from h2 close to comma infinity, that is also non-negative function, by f of x is equal to, note that fk does not converges to f. Limit infimum of fk goes to f. So this is what they have given. So if these hypotheses getting satisfied, then we have to show that f is s measurable, and also we have to show this integral f d mu is less than or equal to limit k goes to infinity infimum of k goes to infinity integral f k d mu. So for saying f is s measurable, this is easy part, so you can do it. This part is the most main for the, this is the main for proving this Fatou's lemma. Okay, so let's go. Don't panic about this many statement, so the proof will be quite easy. J greater than or equal to k. So for each k, so they are fixing some k. So after this k, every value will be j. Okay, that is j for all j greater than or equal to k. So for all these values, we have this inequality. Okay, so this inequality also I'll explain. Okay, if you want to know what is this inequality, let's go with the base. Let us see the proof. For each k, we have all j greater than or equal to k such that infimum of fn is less than or equal to fj. Don't worry, I'll explain everything. Okay, j basic elementary thing, k equal to 1. So suppose, okay, so for each k, we have all j greater than or equal to k. So all j greater than or equal to 1, we have such that what we have infimum running on n greater than or equal to k. K here is 1. Fn will be less than or equal to fj. What is j actually? Fj will be greater than or equal to 1. So it will be f1, f2 and so on. So we have in the left hand side it will be f1, f2, sorry, in the right hand side. It's not in the left hand side, it is in the right hand side. Because it is for all j, right? So all j greater than or equal to 1. So f1, f2, so on. This will be in this place, which will be greater than or equal to infimum over n greater than or equal to 1 fn's. Okay, so you should obviously agree this inequality. So that is what we have written. Okay, for k equal to 1, this is okay. What about k equal to 2? When k equal to 2, you have for all j greater than or equal to 2, because k here is 2. Okay, so infimum of n greater than or equal to 2 f n is strictly less than or equal to fj. So what they're basically doing is very simple. See, if you have a set S, okay, so will you be convinced with this notation? Infimum of S less than or equal to the set S. Okay, this is for, maybe we have this set of elements to be n, maybe. I can also, so this is what they are doing. But what they are ultimately doing is, firstly, they are, suppose this is my f1, f2, f3 and so on. So what they are doing is, for the first step, they are doing for the infimum of everything, f1, f2, okay, will be less than or equal to same f1, f2, so on. So this is the first step. For the second step, what they are doing is f2 is less than or equal to here also f2 and so on, f2, f3 and so on. So this is what they are doing. So if you are convinced with this argument, then you can obviously follow this one, right? So this is the whole explanation of one particular inequality. But if you are clear with this, let's proceed to the next. So fine. Now because you have this, you should know this, okay? F less than or equal to g, then this integral follows from the monotonicity property. That is, if f less than or equal to g, then integral g d mu will be less than I'm sorry, this should be integral f d mu is less than or equal to integral g d mu. So this is a property, you should know this. Okay, fine. So we are going to take, let me write in the red color pen the real proof, and the hint will be in the green pen. Okay, fine. Less than or equal to integral. Okay, when we are taking integral, we have to do with respect to some measure, so I have to put d mu. Okay, fine. So far we have done the things like this inequality, and we have just used the integral property, so nothing more. Okay, will be less than or equal to infimum of j greater than or equal to k integral fj d mu. Okay, so this inequality you should be clear. Okay, actually from this step to here, we have to write this is for all j greater than or equal to k, because we have to imitate that step, right? So that's what we have done here. Fine. Now you should know that this is the lower bound for this. Okay, because this is less than or equal to this for all j greater than or equal to k. So this will be the lower bound for this part. So what we can do is, whenever you are taking infimum, you have to say for on what. Okay, so I should have written there. Okay, this sequence is actually monotonically decreasing. Okay, what we have taken? Monotonically non-negative S measurable function. So we have constructed it in a way that it is monotonically non-decreasing function. Okay, in k. So what we can apply is, we can now apply what? Monotone convergence theorem. Because for the monotone convergence theorem, we need the sequence to be non-decreasing sequence. Okay, so that's why we have constructed. They haven't given you a non-decreasing sequence. Okay, they just gave you non-negative S measurable function. So from that, we have constructed a non-negative, non-decreasing sequence. Okay, so now we can use the monotone convergence theorem. I will tell you the statement of monotone convergence theorem. But before that, let me write the result here. Limit infimum k goes to infinity fk d mu, which is equal to, see, this theorem is important. I will also prove this theorem. Okay, so limit k goes to infinity infimum of n greater than or equal to k fn d mu. That is nothing but limit k goes to infinity integral, don't worry, I will explain you everything, fn d mu. Okay, I will explain you monotone convergence theorem also, and I will also say you some hint. Okay, so I have written the reason also here. Okay, since the sequence infimum of f of increasing sequence, so see, 0 less than or equal to f1 less than or equal to f2 and so on is an increasing sequence of S measurable function. Define f is from h to close 0 infinity by f of x is equal to, so this sequence converges to f of x. When these things happen, then we can interchange the limit and the integral. Okay, so that is what monotone convergence theorem states. But if you want to use the monotone convergence theorem, you should have the sequence to be not just a non-negative sequence. It should also be an increasing sequence. Okay, so I'll also explain this theorem in the next video. So also I will make sure that you can understand, distinguish between the theorems, because there are a lot of theorems, so you might feel a bit hard to memorize things. So I'll make you to understand the context so that you don't have to memorize. So you can have a look at on the next video. Okay, for understanding this monotone convergence theorem and so on. I'll also prove some Holder's inequality and so on. You can watch that. Okay, so this is the theorem statement is. So you can see where I have used this monotone convergence theorem, because I have used here. Okay, I have taken this limit to the outside. So what I got is, which will be less than or equal to limit k goes to infinity infimum of j greater than or equal to from, because we have first argued that only. Okay, in the beginning of this proof, we have started with this inequality, right? So this inequality just came by I have explained you well, so you would have known now. So this, from this inequality, you have just applied the integral. Sorry, this is the inequality, so you have applied the integral because this is an integral property. And then since this is a lower bound, so I can write take infimum. So I just got this inequality. Okay, so this is the inequality that we are using right here. Okay, so from here to here we have just used that inequality. Relax, we are going to arrive at our destination. Yeah, limit infimum of, this is limit infimum k goes to infinity integral f k d mu. Okay, so okay, you should, so from here to here, this is the definition of the limit infimum. So this is how the limit infimum definition is, so you should know that. Okay, fine, so just we got what we wanted. Okay, fk d mu is less than or equal to limit infimum of k goes to infinity integral fk d mu. So this is very simple, but you should know certain things like this thing, and also you should know monotone convergence theorem, and also you should know, for monotone convergence theorem you need a sequence of increasing, a non-negative increasing sequence. So that's why we have constructed a non-negative increasing sequence. Okay, and also you should know this inequality, because from this inequality only we are developing the proof, and the proof is simple, but you should know certain logics. Okay, and this is a statement again. So we have proved